Yeah. Okay, first of all, I would like to thank organizers for inviting me to take part in this wonderful workshop and for giving me this opportunity to present my recent work. My talk will be based on a series work in collaboration with my collaborator over the recent years. They include Christophe Delapa, Gregor Kailin, Raphael Porto, Jacob Neff, and Zhixin Yang. So this talk will about overall review about effective field theory for two-body problem as well as recent progress. So as we know, so the first direct detection of gravitational wave from binary system marked that so we enter new era of gravitational waves gravitational wave science. So typically the evolution of a binary system consists of three phases: inspiral, merge, and rundown. So in inspiral phase, so the two black holes or two neutron stars, so spiral around each other, and then in this case they lost energy and the distance between them becomes smaller and smaller. Finally, they merge, they collide, and after that, after shorter oscillations, they form into a stable single object. So this is called rundown. Because of Einstein equations are highly nonlinear, so we have to use different methods to deal with different phases for their motions. For rundown, we can use black hole perturbation theory. And for merge phase, because of interaction is extremely strong, so normally we can use only numerical simulation. And for inspiral phase, for this phase, it covers a large number of orbital cycles. So this leads to numerical simulation is inefficient. But in this phase, in particular, in early phase, so interaction because of the distance between two bodies is large. S is, for example, is R. R is large, so interaction is weak. So that means the perturbation theory works. So normally we can use different perturbative expansions to solve the motions for inspiral phase. So in particular for case of velocity, the relative velocity between two bodies is small. In this case, we can solve equation of motion in an expansion of V. It's just a post-Newtonian expansion. So which expansion in V or Newton potential. So so in this table, so from left to right, this is the post-Newtonian expansion. For example, leading order is just a constant order. This is just Newton gravity. And for first corrections, this is v squared, and if we because of this relation, if we identify g as v squared, these two terms in the same order, so they contribute to first corrections in post-Newtonian expansion. So we get 1pn, and this is 2pn, 3pn is this, and 4pn, 5pn, 6pn. So we can also expansion in only Newton constant. In this case works for any values of velocity. This is called post-Minkowski expansion. So this is just the expansion in Newton constant. So this order is g squared, g cubed, g fourth, g5, and g6. So we get this just the 1 p.m., 2 p.m., 3 p.m., 4 p.m., and 5 p.m., and 6 p.m. So the properties of post-Newtonian post-Minkowski expansion is that it works for any values of v. So it's purely really relativistic. So that means QRT method works perfectly. I will show you later. So, and an interesting observation is that for example, for 1 p.m. and 2 p.m. order, so the result contain only is proportion to just the proportion to nu zero. Nu is just mass ratio. We define this mu and mu over m. This mu is reduced mass. It's just the total mass. So 1 p.m. order and 2 p.m. order result contain only nu zero means is nu zero order up to some constant, up to some overall constant. And from 3 p.m. and 4 p.m. order, so the first correction in nu means linear corrections appear for the first time. And from 4 p.m. and 6 p.m., so nu square term also appear for the first time. And from 6 p.m., 7 p.m. and 8 p.m., nu cube term also appear. So we can also organize our calculations in expansion in nu. So this is also this is self-gravitational self-force expansion. So this is just the expansion in nu or in Q. Q is just the mass ratio. For example, M2 over M1. This is reduced mass over total mass. So we call this order, in the leading order in self-force expansion, 0 SF. It just describes the geodesic motion of a small body moving around the Schwarzschild metric. And the first correction in nu is we could 1 SF. This is 2 SF, 3 SF, and so on. And last week, Radu Roiban gave a lecture about using scatter amplitudes to solving this problem. We'll give my talk will talk about effective theory. Yes. Yes. Thanks. So now I will talk about before that I will give a plan of my talk. So first part I will give a introduction, a brief introduction to Wordline effective field theory formalism. So, and then I will introduce some advanced Feynman loop integration tools to solve these problems. And after that, I will present our recent progress. In this field. Finally, just a brief conclusion. And outlook. Okay, let's follow this. So in Inspiral phase, so as I mentioned before, because of interaction is weak, so we can write the metric as a flat space metric plus a small factorization h mu nu. H mu nu is much smaller. So and then effective. The idea of effective theory is very simple. We just if we just integrate out gravitational fields, this h mu nu from full action. So this part just describe two black hole or two neutron stars. This order actions, and this is gravitational actions. So this part include famous Einstein hybrid actions and some like gauge fixing, because Einstein gravity has a large gauge redundancy. So let me introduce this. So because of distance of two black hole or two neutron star is much larger than their size, so we can use a point particle approximation to describe two bodies. So this. So new. So this action just describe point particles, non-spinning point particles, and we can include also like other terms to describe spin effects or tidal effects. Okay, for this I will talk later. And here I just use Polyakov action. The advantage is that in this action has only coupling between worldlines and gravitons. I mean, only a linear coupling. So this method was introduced by Goldberg and Ira Wiston. Actually, in the context of post-Newtonian expansion, and recently we introduced this method to post-Newtonian expansion. So I forgot this. This just gave effective action. So next, the task becomes how to compute effective actions and compute physical observables. So in the we can use perturbation theory. For example, we can use PM expansion. The idea is just we do PM expansions for every quantities. For example, for effective actions, we can formally expand in this way. High order. And for example, for trajectories in the coordinates for two bodies, we can also this is just the initial positions for the bodies I, and this is initial velocity. And this part just describe a free motion. And this is gravitational corrections. We denote this, for example, G square, and so on. Scattering only for, yeah. Yeah, and then we can, for example, we can solve equation of motion for trajectories. So because this part, this just describe free motion. So Lagrangian just eta mu. So if we use all Lagrangian equations for two bodies, means for orderly Weisbors, we can derive equation of motion. This term just from this one, from this part, and we write other part on the right hand side. So there is minus n into mu. So it's just, and if we can also because we do not include so what Weisbors in path integrals, we just use classical equation of motion. Of course, we can also use, for example, we can also and dxi and something, and then take a classical limit. Actually, this is just the idea of so-called WLQFT developed by Jan Plewka and collaborators Morgu, Plewka, and Jan Steinhoff. So from effective actions and from equations for motion for worldlights, we can compute physical observables. For example, we can compute important observables in the scattering, like means momentum change of momentum from initial to final state, just as like pi from final state to initial state. So how to compute this? For compute this, we just need to do an integration from for dxi and m. So this part is given by this. dt. So because of this term just contribute boundary, so it's 0. Okay. Okay, and then the next thing is how to compute effective actions. To compute effective actions, we just use standard textbook method, means Feynman diagrams. Use Feynman diagrams for, first of all, let's have a look at our Lagrangian, our worldline effections in early system. Because of this is eta plus h. So this term give a coupling between graviton and worldline, and because of we do not include our worldline in past integral, so we just consider as the classical source in past integrals. So this gives a vertex between worldline and graviton. We use this ball as worldline. For example, this is I, this graviton mu, momentum is q. So this vertex just mi, kappa. Kappa just Newton constant d tau. This is a Fourier transformation. 1, 2. This? No, this is expansion. Yeah. Yeah, I is 1 and 1 or 2. So and for graviton, and for Einstein actions, if we expansion in this way, we can have so h squared term and h cube term, h force term for n number of graviton terms. This just gives a graviton propagator. This gives vertex. So because we are interested in only classical physics. So we use cycle point approximation in path integrals. So this means, so in Feynman diagram expansions, we just consider classical Feynman diagrams. Means like this is simplest Feynman diagrams, is tree diagrams, just 2-point diagrams, and 3-point diagrams like this. 4-point diagrams. And for example, we never consider this kind of diagrams. Oh, sorry, it's ugly. So this is a graviton loop. So just this diagram contribute only quantum gravity. So this makes this method is highly highly efficient because one hand we can use we can use QFT method to compute to do calculations because we know QFT is a very symmetric method, and on the other hand, because we are just interested in classical physics, so we keep only classical contributions at every step. This makes calculation much simpler compared to for quantum calculation. Sorry? Yeah, this is the graviton, and this is what Q is momentum. Sorry? This is the water line. It's just this object. Because in these actions we have T. Actually, yes. Okay.
As you said, this is very efficient because you only get classical diagrams. But then you have two methods here. You have the rotational motion versus one of which one of those is
So yeah, for what like QFTs, they can I will show you later. So for example, so in our method, so this simplest diagrams in the tree diagram. The tree diagram. This diagram contributes to any order in PM expansion. Means in higher order, it enter result in iterations. So in our method, the iteration just from solving equation of motion. But in ordinary QFT, they can organize all iterations in a graphic ways. So I mean the difference just in generating integrand, and for this part it's not challenging. Sorry. Mm-hmm. I didn't talk about this. Yeah, for here we just yeah for graviton propagators, is momentum p. It's just a tensor, and if we use, for example, if we use Feynman I epsilon, in this case, this case only can describe a conservative. If we include the deceptive result, we have to use retard propagator in the p minus plus. Yeah, if we have time, if I have time, I will. But I guess I have no time to talk about that case. Sorry? You mean what line? Yes. 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 Yeah, exactly same. The difference is. Sorry? Of course. Of course. Yeah. The only difference is in our method we use classical equation motions. In their method they include what line variables in path integral. Yes, yes. So now I will use an example to show how our formalism works. So let's just consider this simplest diagrams. That's the tree diagrams. This gives one and two. This from minus infinity to plus infinity. And this is a Q. We use Dimrag. sorry, use K, Q. So, and from these diagrams, we can we can compute also inputs, means delta P. For example, delta P1 just gives. So this part is same. Sorry, it's not. Oh, yes. This gives a I Q mu because of there is a derivative. So from important properties is these formulas and this formula are exact to any order in G. Sorry? I'm sorry. X1 dot is dx1 d tau 1. X2 dot is dx2 d tau 2 is different. Oh, sorry. Yes. Square. Okay. Yes, important properties is these two formulas are exact in any order. I mean, from this type, we do not do any expansion. And then we can solve it by y expansions, like for example, PM expansions. For example, if we expand. Sorry?
I mean, what does it mean, exacted in order? I mean, you haven't specified what x of tau means.
For example, so for this diagrams, there is overall factor of G, right? But here, sorry.
There's g's inside x.
Yeah, exactly. So it means x and x dot are exact in any order. For example, we can expansion in x. Yes, and higher order. Yeah, for example, if we keep only leading order, means this part we can get 1 PM result in the leading order. The equation of motion becomes for example, for particle 1, so this is impact parameter, means B1, B2, B1 minus B2, means distance between two bodies. Okay, and so this delta functions because of these actions has twofold of integrals over d tau 1, d tau 2, and if we compute this guy just from integration for d tau 2, because I will so give a delta functions, and important interesting thing is I'm sorry, it's not, and I sorry. So, and the important thing is because of in the boundary means when, for example, in tau in the initial stage, so this part should be 0. So we have so in this, so this means we must include I epsilon here to make sure it vanish in the infinity past. And if we solve this solve this equation of motions, we can get velocities and a position. This we can get this just do integration over tau 1. So for tau 1, we can get additional propagator from here in q dot u minus I, like this. So I will do not write down the formula, and for this we will get anyway. So basically from these actions we can solve here where I have shown we can solve leading order equation of motions, and then if we plug if we plug leading order solutions into like for example into these formulas, we can compute subleading order, means T square terms. Iteratively we can compute all order contribution from these diagrams. Sorry. Yes. Yes. Yeah, because for example, if our goal is to compute these observables, so for there is a G, there is overall G. If we use leading order trajectories, we just we can get leading order means G. If we include the next leading order corrections for trajectory, here we can get G square and G cube something. I think it's non-trivial. Yeah, that is. I think just in last week there is paper discuss the equivalence between them. So of course I just discuss these simplest diagrams. Of course, in principle we need to conclude more diagrams. Yeah, for example, if we compute subleading order result, not subleading, next to leading order in T squares, in addition to these diagrams, we need to also consider these diagrams. This compute, and if we want to compute G cube, we need to consider this kind of diagrams. So from here we can say if we compute leading order 1 p.m., we just need these diagrams. If we want to compute 2 p.m., we just need these diagrams and this diagram, 2 diagrams. If we want to compute 3 p.m., we just need this one and 5 others. So in this case, we just need to compute 7 diagrams. So this is what I mean. So this formalism is very efficient. And now I just write down the final structure. For example, for these quantities, at any order, like at Gn order, this quantity has this structure. So this one just the Fourier transformation. It just transform result from momentum space to the space of impact parameter, and this is a loop integral. And actually, this part is normally trivial. So if we want to compute Gn order inputs, the hard thing is compute n minus 1 loop integrals. And here, so in our formalisms, each loop integrations will always have delta functions. This is called propagator, and this is Gravitational propagator.
How would it differ if you try to do a bound system? So I think your first formula is still valid for a bound system, right?
No, for scattering.
Oh, but we haven't specified what x is in the first formula.
This formula? No, I don't think so. It's scattering. Maybe, but for bound systems, for bound case, we don't know how to define initial conditions. Maybe. Okay, now I introduce some integration tools to compute that loop integrals. So our loop integral has this form. This contribution to npm order means Gn. This u just the initial velocity a is 1 or 2. Sorry?
Diagrams themselves, they don't tell loops. So the looper comes from the integration of the
Yes.
but the diagrams are all trivial, right? Just faster.
Yes. From this one, you can, for example, so so from this one, so this formula has a this formula has the one for the has the one for the of loop integrations. If we compute only leading order, it's just a purely Fourier transformation, right? And for example, if we consider and for next leading order correction for trajectory, so this one means the equation of motion include one fold of integrations for momentums. If we plug this one into this, so it becomes two for the integrations. One fold becomes Fourier transformation. Another one becomes loop integration. So for these integrals, first of all, for delta functions, we can use these identities. So in this way, we can deal with delta functions just as ordinary linear propagators, and then standard technology from particle physics can be used directly. So firstly, we can use IBP. I just very briefly describe it. For example, for many integrals, we can reduce to a small basis, I1, I2. So normally this n is small. And how to compute this means mass integrals. So another problem becomes how to compute mass integrals. So the most powerful method for this kind of integral is differential equations. The idea is very simple. For example, if we derivative for this basis, for example, for some mass integrals, so this will generate arbitrary integrals like this. This one is not normally this one is not mass integrals, but we can use IBP relations to pull this back into mass integrals. So finally, we can get a system like this becomes mass integral again. So IBP equations can give us give a system differential equations for mass integrals. So, and important developing for solving differential equations for Feynman integral is that is that Johannes observed if we can, for example, if we if we can find a basis, a transformation for our initial basis is f. If we can find a transformation like t, a new basis g, if in this basis differential equations become simpler, means differential equation matrix matrix for epsilon dependence becomes simpler, means it factor out from matrix, and then we can formally solve these differential equations. For example, if we write it as expansion in epsilon, and then we can solve this. We can solve it order by order in this case. Because there is the overall epsilon factors. So if we compute like a GK order, so in this case, the right hand, we just need to consider GK minus 1 order. So we can, in this way, we can construct the solutions order by order in a systematic way. So in particular, if this matrix has a simple pole, so in this case, this solution is a chain iterated integrals. It is also known as multiple pole logarithms. And recently we found if differential equations include elliptic cases, we can also compute. We also managed to compute it. I will show you later. So the last thing is to compute this boundary constant. So to compute a boundary constant, we define it in post-Newtonian limit. Means, for example, we introduce some this gamma just the Lorentz boost factor is u1 dot u2. U1 and u2 are initial velocities. It's just so post-Newtonian limit just v goes to 0, means gamma goes to 1. So in this region, we can compute. We can define. First of all, we should use the method of region. So Anna Gadi discussed this method in the first week of this conference. I want to not give more details. I just introduced, because of our method, our formalism is purely classical. So all our integrals land in naturally in classical in soft region. Soft region means for example, this is momentum carried by graviton. Graviton so has a over. This is the loop momentum of gravitons, and this is momentum transfer has this. This is much bigger than P1 or P2. P1 and P2 just the momentum of two massive bodies, means black hole or neutron stars. So soft region can be classified into two different regions. One is potential region. So for potential region, so this is the momentum. This is the energy component. This is the momentum component. For soft region, this is much smaller than this. So we can, like this Q. This Q is momentum transfer. This is small because we use the post-Newtonian limit. So V is much smaller than 1. So for potential modes, they just carry, so for potential case, they're just space-like, and for radiation region. For radiation regions, momentum components and energy component and the momentum component has the same size. In this case, it can be on shear. So using this method, so for example, for integral, if we analyze all possibles for all propagators or for all loop momentums in different regions, we can identify a set of independent regions, and then we can expand our integrals according to different regions. After that, we can compute boundary constants. So I want to not give more details about this, but I want to say, so from post-Newtonian physics, means we can bootstrap post-Minkowski physics from post-Newtonian physics via differential equations. Sorry, D. So next, I give some, I present some our recent progress. Okay, first thing is to include like spin effects. Yes. Yes. Sorry? Mm, yes. So to include the spin effects, we have to go to go to locally flat framework. Means we need to go to something. We need to introduce this kind of metric. Yeah, and then we can define a spin, for example. So this is just a linear coupling between spin and the word lie. This is just a spin connection. Of course, we can include a high order in spin, like for example, spin. To include the spin square contributions, we have to use wire tensor. So this is why. Yes. So this term describe a spin square, and of course we can include more order in spins. For anything. What do you mean it's clear? Yeah, I'm sorry. We should. There is no, sorry. Here, there is a there is a Western coefficients like CE. Yeah, if C is one is for C is one is for neutron star. It's zero for black hole. Sorry.
I see two terms instead of that. So is that two coefficients or one coefficient?
Only one.
Only one.
Yes.
What fixes the relativity?
This is fixed by SSC. Mean. So in this paper, we compute next to leading order result up to spin square. And from spin, this is spin tensor. From spin tensor, we compute spin vector anyway, spin vector, spin tensor, and spin tensor. This is a spin tensor. This spin vector. So because of this vector also need to satisfy this condition. So this also I mean this only have three physical component means x, y, the ordinary spin. And recently, if we impose SSA, means we have only this term, but recently we can if we give up these conditions, we can include other terms. By the way, and other in a recent paper. So it's very interesting to study properties of this kind. Okay, now I will go to next leading order, for example, T3 order, 3 p.m. In this case, we need to compute. Okay, I have eraser. We just need to consider seven diagrams, and all integrals. All integrals has this topology, in the this is one. Propagator is just D1, D2, D5, and also this canal propagator L1.U2. D1, D5 just defined by gravitational propagators. So for this case, it's very easy to find Ipton factorize the differential equations in this way. So here, A, B, and C just the matrix with rational numbers as entries, and so finally, if we solve this differential equations, so we can have a result for any integrals in this family. So result. Sorry. 8 master. So yeah, and then we reproduced the 3 p.m. results, which gave first classical confirmation for the way result as a result of obtained by the way and the friends. So if we go into next order means G fourth order for PM. In this case, most of integral can be solved in Epsilon factorized differential equations, but there is a diagram like this. The actually is topology. So in this topology, there is this topology cannot be solved by ordinary Epsilon factorized differential equations because it contains elliptic integrals. In this case, I just maybe I. Okay, for this diagrams, it in top sector there are 3 mass integrals. So our strategy is solve it in leading order in Epsilon, like we get these differential equations. Okay, I will do not write down all entries. They are just the rational functions in X, like this one. It's just the leading order in Epsilon. So our strategy is we can transform this system of 3 first order differential equations into one third order differential equations. Like this. The form is this. For example, F1. So it's very interestingly, we found surprisingly that it's very easy to solve this. Okay, to solve these differential equations. For example, if we use Mathematica, you can find 3 solutions in 1 second. This solution just in this. Here K just the K just complete elliptic integral of first kind. This. And then, so if we use these technologies, we can our strategy is to construct answers for differential equations. But this case, in this case, differential equations will include information about information on these solutions, and then we can transform differential equations into Epsilon factorized form. Means I just write down in the forms here. Just we goes from F basis to go to a new basis, G basis. Go this way. This elliptic means. In this case, this matrix, differential equation matrix, include the information of solution. So I want to not write down other entries, but I just want to say, so in this case, entries include the leading order solutions. And then for higher order in solution can be written down in iterated integrals. But in this case, integration kernel include elliptic integral. So with this result of integrals, we finally compute full contributions for 4 PM dynamics for Inspiral phase. Because we have no slide. No, I will do not. Okay, I will stop here. Thanks. So basic idea is we use initial algorithms. For initial algorithms, first of all, we must have an initial integral that must be pure integrals. In this case, we just, for example, because this at leading epsilon order, this integral has 3 solutions, right? Like this way, for example, we can construct an initial integral in this way. G1 is just like, for example, if we modular this solution. So in this, because this is a solution for F1, so and then so for G1 integrals, so at leading order it's just a rational number. It's not elliptic again. So we just guess this is a pure integral, and we use this as the initial integral to construct this matrix. Third ODE. You mean from this to this? This is simple. First order. Because yes, three first order differential equation can be transformed into 1 third order differential equation. In general, a system of n first order differential equations can be transformed into 1 nth order differential equations, right?
So, do you ever encounter unit divergences?
UV component.
Or do you expect the quantum UV divergence higher than
I don't know. I think, but at 4 p.m., I think we have IR divergence.
Yeah, that's why I'm asking about. But if you include like tidal operators, do you see UV divergences earlier?
If we can do tidal effects, I think UV divergence may appear at 4 p.m. order.
At 4 p.m. the earliest, or would it appear even lower?
3 p.m. order, I don't think so.
Thursday we are going to be in the improvement area.
Remains to be good.
This one, yeah.
就是我椭圆函数，你说这个椭圆函数它耦合了很多个，那就是说你要解了就会变成一个 n 乘的这种。耦合了。